This time we're going to talk about the Rankine cycle with reheat. So how can we increase the thermal efficiency of our cycle? One way we can do that is by increasing the work output of the turbines with reheating, and that will increase the work net output and thus increase the thermal efficiency of our cycle. So what we're going to do, we're going to follow along on a TS diagram and look at how this cycle looks. From 1 to 2, you have an ideally isentropic expansion or isentropic compression within a pump. Of course, if you have an isentropic efficiency less than 1, you'll have to account for that. Then you have a constant pressure heat addition process within a steam generator. And then, so far it kind of looks the exact same as the simple Rankine cycle. Then you have an expansion within a high pressure turbine to state 4. So on a TS diagram, you see it goes straight down, but it doesn't go all the way down to the pressure at the inlet of the pump, state 1. So what we're going to do from 3 to 4, we partially expand it, then we take another pass through that steam generator, we reheat it up, and then we fully expand it in the low pressure turbine so that P6 and P1 are exactly the same, and we go through a constant pressure heat rejection process and a condenser. So let's look at where our pressures are equal. P1 and P6 are equal, P4 and P5 are equal, P3 and P2 are equal. And that comes from assuming that there's no fluid friction, which would cause pressure drops within our cycle. We have increased the enclosed area as compared to a simple Rankine cycle. And so the net Q in and thus the net work out has increased. The other thing that we've done is we've kind of pushed things out to the right so that we're not in that two-phase region. We could still expand into the two-phase region, but it's a good idea to limit how far you go into that two-phase region, because the appearance of liquid water droplets can cause physical damage to your turbine blades, especially at the exit. Those turbine blades are, they will be rated to withstand a certain amount of liquid water droplets, but you need to minimize it. And the manufacturer will tell you how much the minimum or the maximum, the minimum quality that you are allowed to have at the exit. So your book says a good rule of thumb is keeping it above 90%. A better rule of thumb is looking at the manufacturer. What do they suggest for their particular turbine blades? Because it'll depend on the type of turbine and the application that it's designed for. Let's see, anything else? I guess not. So let's look at how we analyze that steam generator. All the other devices in that cycle, you know how to analyze. And you know how to analyze this too. It's just one little level of complexity. So you know how to analyze the pump, you know how to analyze those turbines, the condenser. Let's look at the steam generator because it's a little bit more complicated. So if I drew my control volume around this steam generator and I applied my first law, everything's operating at steady state. That's the way all of these cycles are going to be operating in this class. And I don't have a Q out, I've got a Q in. I don't have any work. I'm not going to consider kinetic and potential energy changes. And so all I've got is Q dot in equals the sum of the M dot H's coming out minus the sum of the M dot H's going in. And it looks like for this control volume, I've got 2 inlets and 2 outlets. So I've got things coming out at 3 and 5 and things coming in at 2 and 4. And then because that cycle is just operating at steady state and it's one big closed loop, the mass flow rate is the same everywhere. So M.3, M.5, M.2, M.4, those are all equal to one another. And then I could divide through by M dot if I needed to get things in terms of little q, which would be kilojoules per kilogram. So one thing to note with a Rankine cycle with reheat is that because within that steam generator, because I have I've got steam from 2 to 3 and 4 to 5, both pulling heat or both using that Q in, I have to account for that. So a Rankine cycle with reheat does require an additional Q in, but the increase in the work net out more than compensates for that. And so the overall effect is an increase in thermal efficiency. So a Rankine with reheat does require more Q in, but the net effect, because of that work net output increase, is an increase in thermal efficiency. All right. Well, I hope that was helpful. Thank you very much for watching.